Greetings, Math 243 students, and welcome to the binomial distribution. Very exciting day. All right, let's go ahead and get started talking about the binomial distribution. So the binomial distribution is just a special type, a very commonly used type of a discrete probability distribution function. So what we learned about in 4.1 and 4.2 is all going to apply to the binomial distribution. This is just a special one that we use a lot. For this one, we're going to do a number of trials of an experiment. Each repetition of the experiment is exactly the same as the previous one. Nothing changes between the trials. And the letter N is going to denote the number of trials that we do. In this type of experiment, there's only going to be two possible outcomes. You're either going to have a success or you're going to have a failure. So the letter P is going to denote the probability of a success, and the letter Q is going to note the probability of a failure. And note that, of course, P plus Q would equal 1 because they're complements. And the N trials in the experiment are going to be independent and repeated using identical conditions. So there's nothing going to change between the trials of the experiment. All right, so let's look at some examples. Maybe we're going to flip a coin a whole bunch of times in a row. Each coin flip is a trial of the experiment. If it's a fair coin, it would be 50% chance of success. And the number of trials depends on how many times we want to flip the coin. Another example would be if you're taking a true-false test and just guessing the answer. The number of trials would be the number of questions on the test. Each question you guess with a probability of success. Basically, anytime there's going to be two outcomes in a series of trials, and one could be thought of as success and one's failure, it's going to be the binomial distribution. Let's talk about the notation just a little bit. Remember, the binomial distribution is going to be a distribution on a random variable. We use capital X. And in this case, X is going to be the number of successes obtained in N trials. Okay, that's always going to be X for the binomial distribution. Again, N is the number of trials, P is the probability of success, and Q equals 1 minus P, the complement of success, which is failure. A little bit more notation. Oftentimes you'll see binomial distribution represented with the notation B, NP. So the B is just to indicate that this is a binomial instead of like a Poisson or a geometric or other things we're going to talk about later. B, and then N is going to be that N up here, the number of trials, and P is the probability of success. And of course, we don't need to write down Q because we can quickly compute it by subtracting P from 1. All right, so let's just do an example, making sure we understand the setup here. So a trainer is teaching a dolphin to do tricks. The probability that the dolphin successfully performs a trick is 35%. And the probability the dolphin does not perform the trick is 65%. Out of 20 attempts, we want to find the probability that the dolphin succeeds 12 times. So first, what is our random variable here? What are the values of N, P, and Q? And let's finish the notation. Why don't you pause the video and see if you can fill these things in for yourself? All right, are you back? Well, X, the random variable, is the number of times the dolphin successfully performs a trick. Remember, that's always going to be the flavor of our random variable for binomial distribution. The number of attempts was 20, so he tried the trick 20 times, or she. The probability of success was 35%. The probability of failure was 65%. And if we wanted to write this in binomial notation, we'd write B 20, 0.35. I'm not going to answer this question right now, but you can come back to this later and figure it out. In just a few minutes, you'll be able to do this. All right, let's now learn how to compute some binomial probabilities. Let's start with an example. A fair coin is flipped 15 times. Each flip of the coin is independent. So that means, again, that what you get on one flip is not going to affect what you get on the second flip or the third flip, etc. All the flips are going to be the same probability of getting heads. What is the probability of getting 10 or more than 10 heads in these 15 coin flips? Well, the way we're going to set this up to be a binomial distribution is we're going to let capital X be our random variable, and that's going to be the number of heads in 15 flips of the fair coin. Our random variable, capital X, will take on any value between 0 and 15. So 0 would be the case where you got all tails every single time. So this guy is it always does that. Hang on. All tails, which is possible, not probable, but possible. And then 15 would be the one where you got all heads. Like every time you flipped it, it came up heads. And any of the values in between, discrete values in between, are possible. So you could have 3 heads and 12 tails, etc. Since the coin is fair, the probability of success is a half. and the probability of failure is a half. And the number of trials we're going to be doing is 15. So we're going to use Desmos to help us do this computation, and we're going to use this built-in function called binomial dist. So let's go ahead and do that now. So what I want you to do now is go to our MyOpenMath page. Yes, our MyOpenMath page for this class. And under 4.3 video lecture, where you started the lecture, you'll see a link that says example 1 in Desmos. Go ahead and click on that link. So here we have the setup. I just typed this in. A fair coin is flipped 15 times. Each flip is independent. What is the probability of getting more than 10 heads? So what we're going to use for this is we're going to do the setup that we have. We're going to use a function called binomial dist. I'm going to actually delete the rest of this so we can see what this looks like as we type it in. When you type in the function binomial dist, let me just bring it up. It gives you some, and you do a left parenthesis, it gives you some hints about what you should be typing in. The first thing it says is trials, and then the second thing it says is success probability. So in our case, we're flipping the coin 15 times, so we put in 15 for the number of trials. I'm going to unclick that for now. And our success probability is a half because it's a fair coin, so 0.5. So we put that in, and that's our binomial dist. And then there's a choice down here that says find cumulative probability. And we actually are going to just leave that for now. I'm just going to hit enter and turn that on. And let's go ahead and see this zoom fit button. Let's go ahead and hit this. So here's a picture of our binomial distribution. And each one of these green dots represents a number of trials, anywhere between zero successes out of 15 trials or 15 successes out of 15 trials. And if you can zoom in on these guys and you can see their probabilities. So if we want to know the probability of getting exactly 14 heads out of 15 trials, it would be 0.0005. And in fact, it shows 0 for getting 15 heads out of 15 trials, but it's really a really small decimal, really unlikely. It just is rounding it to 0. If we want to know the probability of getting exactly 7 heads, it would be 0.1964. So all this is showing you, it's a graph. The x-axis gives you the number of trials, and the y-axis gives you the probability of success for that particular value. Now, what we're asking for here, and a lot of times what we ask for is not what's the probability of getting exactly 10 heads. We're asking what's the probability of getting more than 10 heads. So if you want a range of probabilities, we're going to click this box that says find cumulative probability. Okay. And what is our range that we're going to be computing here? Well, if we want more than 10, so actually 10 isn't the right number here. It should be 11 because 10 is not more than 10. We want to know the probability of getting 11 up through and including 15. And you can see it colors it on your graph. It's adding this probability, the 0.0417 plus 0.139 plus this, plus this, plus this, right? All added up, and that is the value that is listed right here. So the probability of getting more than 10 heads is 0.0592. We'll round to 4 decimal places, all right? So that's our first example about how to use Desmos to calculate binomial distributions. Let's do another example. To load up this example, I want you to go back to where we were and this time choose example 2 in Desmos. All right, so let's try another example using binomial dist in Desmos. An unfair coin is flipped 15 times. So same number of flips, but this time it's an unfair coin. Each flip of the coin is independent. So that means, again, what you get on your first flip isn't going to affect what you get on your second flip. The unfair coin is such that the probability of getting heads is 0.7. Let x be a random variable, and it's going to be the number of heads in 15 flips of the fair coin. Again, x is going to take on the value 0, 1, 2, 3, all the way up to 15. Oh, the coin is unfair. We need to fix this. Unfair. P is equal to 0.7, and that's the probability of getting heads, and the probability of getting tails is going to be 0.3. All right. The number of trials is still 15. All right, so we have a different scenario here. Before it was even heads and tails, and we saw that distribution was a nice symmetric curve. But now it's more likely to get heads. So I don't think we're going to see the same thing, but let's go ahead and get started. What is the probability of getting exactly 15 heads? So I'm just going to hit enter, and we're going to bring up our binomial distribution for this and kind of look at what would it be for exactly 15 heads. So I'm putting in binomial dist. And you know that you got the right one. You typed it correctly if it goes from italics to non-italics. Left parentheses. We have 15 trials again. This time, our probability of success isn't 0.5. Our success is 0.7. Leave the find cumulative alone for now, and let's do a zoom fit. And see, there is our probability distribution function now. It still tells you the same things. My x-axis is still the number of successes, and my y-axis is still the probability of a success. But you can see it's not symmetric about even because it's way more likely to get more heads than not because heads are more likely. So if I want to know the probability of getting exactly 5 heads, I'm going to go to 5 right here. Just click on it again. And it says 5 successes has a probability of 0.003. All right. So that's one way I can do that. So I'm going to type in my answer here. 0.003. And I did that by just going over to 5 and looking at what the probability was. Another way you can do that if you don't want to just do the mouse is we can go to find cumulative probability and just really limit it from 5 to 5. And that rounds 2.003. So that's another way to do that. I kind of like doing it this way because it's just written there. It's easy to look at. All right, next question. Let's try another one. What is the probability of getting exactly 5 or fewer heads? So let's go ahead and enter. And we're going to use, I'm going to turn this one, binom dist, because it'll go on another, it'll make another copy of this right over the other one, but that's okay. 15, 0.7. Let's go ahead and just turn this one off so it doesn't look weird. And we want to know a probability of getting exactly 5 heads or fewer heads. So that's going to be 0 heads, right? Or 1, or 2, or 3, or 4, or 5, right? So you could add these guys up, or you could have Desmos do the work for you. 5 or fewer is going to be 0 up to and including 5. If it was fewer than 5, you'd want to stop at 4. But it says 5 or fewer, so you want to go from 0 to 5. All right. I would like you guys to try to answer this one on your own. So pause the video, hit enter the binomial distribution function to answer the question, what is the probability of getting 12 or more heads? And come back to the video. All right, were you able to do this? Let's give it a try. We're going to go binomial dist. We're going to put in 15 trials, 0.7 probability of success. So this has all been the same because it's been the same setup. We're going to go cumulative probability, and we want to know 12 or more. So anywhere from 12 up to and including 15. So the probability of getting 12 or more heads is equal to 0.2969, rounding to 4 decimal places. Probably should have put the answer into this one. Sorry. We'll put that in now. 0.0037. All right, and now what is the expected number of heads that we're going to get? Well, to find expected value for this probability distribution function, there's a really nice formula for binomial, and I'll go over this again a little bit in the video. But what you do is you take the probability of success, 0.7, and you multiply it by the number of trials. So in this case, we're going to take 0.7 and times it by 15. I don't think I needed an equal sign there. I did it. And we got 10.5. And you can actually see that makes sense, that that's going to be the expected value of success, because it's going to be exactly such that half the area is to the left of this number. If you looked at those values under these curves, half of this probability is going to be to the left and half of it is going to be to the right. And so right between 10 and 11 is going to be our value. But the formula is just equal to the probability of success times the number of trials. I'm going to write that in here. So that's use probability of success times number of trials to find the expected value. All right, let's try one more example. So again, go back to our lecture, to the My Open Math page, and let's look at example 3. So it doesn't have to always be coin flipping. You can apply this to any situation. Binomial always works if you could write the situation as a success and a failure. So probability of getting heads, that works. Getting heads is a success, getting tails is a failure. You could think about doing a true-false test, right? A success is that you get the answer correct, and failure is you get the answer wrong. So that would be, probability of guessing on a true-false test. Anytime there's 2 options and one could be considered success and the other one could be considered failure, you can make this work. So we're going to do an example here. We have 30 people who are exposed to a virus. the probability of catching the virus is 45%. What is the probability that at least 15 people catch the virus? So in this one, I'm going to go ahead and go in here and define my random variable as well. Actually, they're not letting me type anymore for some reason. Okay. We're going to let x equal to the number of people who catch the virus. Now, you may not consider this to be a success, right? In the standard sense of the word success. But we're going to think of it as a success just in our thinking of this problem. A success would be that you catch the virus. A failure would be that you didn't catch it. You could do it the other way around, but they gave us the probability of catching it, so that makes catching it be the success. So x can range from anywhere from 0 people could potentially catch it up to all 30 people could catch the virus. So x is a random variable. It's going to be the number of people who catch the virus. It ranges in values from 0 to 30, from very lucky, no one got it, to very unlucky, every single person got it. And it is binomial because you have a success, you caught the virus, or you have a fail, you didn't catch the virus. All right, so we're going to use binomial distribution for this. All right, so let's go ahead and figure out what is the probability that at least 15 people catch the virus. So we're going to use binomial dist, okay? The number of trials this time, well, 30 people are exposed. Each person is a trial of getting this virus. So we're going to make the number of trials 30, and the probability of success, or the probability of getting the virus, is 0.45, right? And let's go ahead and zoom fit so we can see what this distribution looks like. There it is. And it's pretty similar to tossing a fair coin, because 45% chance, you got a pretty close to 50-50 chance. So it's a little bit symmetric, a little skewed to the left. You can see it's a little less likely to get it than to get it. All right. And we want to know the probability that at least 15 people catch the virus. Not exactly 15. If we wanted exactly 15, that would be about 12.4% or 0.124. We want at least 15. So that means 15 people or 16 people or 17 people, 30 people. All right. So we're going to go from 15 up to 30. So the probability that at least 15 people catch the virus is, let's type our answer in there, 0.0.3552, rounding to 4 decimal places. And how many people do we expect to catch the virus, right? What do we think is going to happen? You had a party, 30 people came, everybody got exposed to this virus. Sounds familiar, right? How many people do we expect to get sick after this party? Well, remember, we use the formula P times the number of trials, probability of success times the number of trials. Well, it's a 0.45 probability of success times 30 people. And we expect about 13 and a half or 14 people. We want to round up 14 people to get the virus. All right. So this is how to use Desmos to help calculate binomials. It's pretty slick, actually. It's way better than what we've done in the past. I did this a little bit in Excel, but I want to review this for you now so you have this written down carefully. For a random variable binomial distribution, and with all these definitions that we had before, the mean, variance, and standard deviation can be computed the following way with these formulas. The mean is equal to the number of trials times the probability. The variance is equal to the number of trials times the probability of success times the probability of failure. And as always, the standard deviation is the square root of the variance. So you are able to calculate those using these formulas. All right, so let's go ahead, and we did this before just in Excel, but let's calculate this by hand. What is the expected number of wins? We're going to use mu equals n times p. So in this one, that's going to be 25 times 0.3897, which I actually have a calculator here today. 25 times 0.3897. Oops, I pushed the buttons wrong though. 25 times 0.3897 is equal to 9.7 games they think they might win. And what is the standard deviation of the number of wins? That's going to be sigma, and that's equal to the square root. Remember our formula right here. Sigma equals the square root of NPQ. N times P times Q. So that's the square root of 25 times 0.3897 times 1 minus 0.3897, which is 0.6103. Using my calculator to compute that product and then take the square root, I take 25 times 0.3897 times 0.6103, and I get the square root of 5.9458, and that is about equal to, where's my square root button on this guy? 2.44 as my standard deviation value. All right, well, that's it for binomial distribution, and good luck with this one. It's a fun one.